All right, in this video, we're going to talk about curves in space. And so what we've got defined so far here is a parametric curve in R3. We've dealt with parametric equations before, back in Calc 2 and then a little bit here in Calc 3 as well. But now we're going to talk about parametric curves specifically in R3, where x is going to be f of t, y is going to be g of t, which nothing has changed there. And then now we have a z component, which we'll define as h of t. So these would be the parametric equations of a curve in R3. Now we'll take it a little bit of a different direction for the time being and introduce this idea of a vector valued function. And so notice the notation here. I do have the vector notation on R. It is going to be a function of t, and we've got our components, f, g, and h, written in component form with the bracket notation. And you can see the x is just the f, the y is the g, and the z is the h. So really not a stretch there to make that connection. We'll call this our position vector. And what it does is it allows us to find or to point to any point along the curve. So let's say that this is our curve right here. We'll call that C. Then our position vector, let's say it comes out and hits right here. That'll be our R of t, and this will be our point that we come up with. And so the point would be the x of t, y of t, z of t. And again, notice the notation on that. So for a different value of t, it would point to a different point on the graph, eventually allowing us to map out the entire curve. And so I'm going to go ahead and clear the screen. We'll take a look at an example here and kind of see how this is built up. All right, so let's suppose we're given this vector valued function here. We've got r, vector r, notice the notation, a cosine t, a sine t, and then ct. And t being the parameter when we take this out of its vector form and go back into its more traditional form. And what I mean by that is we can now say that x is equal to a cosine t, y is equal to a sine t, and z is equal to ct. So if we want to figure out what this graph is, we can eliminate the parameter like we did earlier. So what I would do here is I would divide by a on both of these, and then I'd go ahead and square both of them. And you can probably see where I'm going with this. If I square both sides on this, this will give me now a cosine squared plus sine squared equals 1. Therefore, x over a squared plus y over a squared is also going to equal 1 using our fundamental identity. So that's going to be an x squared over a squared plus y squared over a squared equals 1. Again, that came from cosine squared plus sine squared equaling 1, making the substitutions there and there. And now if I multiply the a squared over, x squared plus y squared equals a squared. And so you might think, okay, great, we've got a circle. Well, we're actually in R3, and so we don't have a cylinder either. What we haven't taken into account is z. Z is going to be ct, where c is just a constant. So what that's going to do is it's going to take our circle that looks something like this, and as we proceed with new t values, it's actually going to bring it up, or I suppose down, depending on the value. And so what we're looking at is something like this. Remember, this is a curve, so we're looking at something like this as it continues. If you look straight down this thing, that's where you'll see that circle. But because of the z equals ct, that's going to continue to make it increase or decrease depending on the values. This is called a helix. The book's got a nice picture of a couple of these. I would encourage you to go back and take a look at the pages 750 in the text, page 750. They talk about the helix, and they've got some pictures there that you can take a look at. But yeah, that's how it all relates, and it's really pretty straightforward. We'll notice some nice applications being in vector valued form many times, and so depending on the context, that'll push us into one direction or the other. All right, so as we just saw how those vector valued functions can be treated similar to how we've discussed things in the past, it's going to now also make sense that some fundamental ideas of calculus can also be applied to them. And so up on the screen I've got some basic ideas here from Calc 1 that we've studied again in Calc 2, and now we're transitioning into these vector valued functions. A couple big takeaways. Let's start here with the limit. So the limit as t approaches a of the vector valued function r, notice the notation, is L, L being a vector itself. This vector, what this says is that the terminal point of r approaches the terminal point of L, both being vectors. The terminal point of this vector approaches the terminal point of this vector as, of course, t approaches a. Okay? The idea of continuity is still the same. We're continuous at t equals a, provided the limit as t approaches a of the vector valued function r equals the vector valued function r evaluated at a. This is a very similar Calc 1 definition, again now just dealing with vectors. The derivative is going to also be the same. I do want to point out that the actual derivative itself, using the limit definition, does result in a vector. And this is an important thing to mention. So let me draw this picture here, and every time I draw it, it appears to be a little misleading, and so let me try my best here. So let's say we have a curve that looks something like this. There's our x-axis and y-axis. And then let's say that this guy right here is going to be our vector r of t. What's interesting is when we take the derivative of this guy, when we result in a vector, that vector is going to be the tangent vector to the curve right here at this point. And so let me sketch this in. So this guy right here would be our r prime of t. Now, where I struggle in drawing this a lot of times is the vector r and the vector r prime are not necessarily orthogonal. They're not necessarily perpendicular, and I've tried to draw it in such a way that this does not look like a 90-degree angle, okay? In fact, most of the time, r and r prime will not be orthogonal. The only time that's the case is when r itself has a constant norm. Well, what does that mean? That means that no matter where this vector hits that curve, the norm or the magnitude of it will be the same. And so you might think of something like a circle. A circle would have a constant norm or constant magnitude for that r vector. And again, that's a special case. That's a very special case, and one that we'll have to discuss quite a bit in a later section. But I just want to mention that so my picture isn't misleading. R and R prime are not necessarily orthogonal. They only are perpendicular when R has a constant norm. The book does a very good job of showing you this. I would encourage you to take a look at page 755. They've got a nice picture in there, and they've also got a nice problem that they've worked out that'll help you see that a little bit better. So I would encourage you to take a look there. All right, so then moving over to the integral. Again, there's nothing really surprising here. The integral of a vector valued function is still adding up infinitely many things to come up with the result. You can see that the result of an integral would be a vector itself plus c, and that c is no longer just a constant, but it is also a vector. We'll take a look at a couple examples of all of these here in just a minute, but this is kind of a nice way to summarize what it is we're transitioning into. I do also want to just kind of say, as I move out of this screen and we look at some examples, that if you're given, let's say, this guy here, f of t, g of t, h of t, if we're looking to find the limit of this or find the derivative of this or integrate this, we're just going to go component by component by component, almost treating this as three separate problems, and then putting the result back together at the end, which, as I pointed out, would be a vector, would be a vector, and would be a vector. Okay?